Swayam Prabha. Digital India. Educated India.
Welcome to the lecture 21 of the course on time series modeling and forecasting. So far in previous lectures on frequency domain analysis, we discussed the role of spectral density function. We also discussed that both time domain analysis and frequency domain analysis provide same information about the time series, but these two approaches represent the information in a different way. So, whether you should go for the time domain analysis or frequency domain analysis, it depends upon your application. What is your emphasis? Whether your emphasis is the evolution of time series through time, or you are more interested in identifying the dominant frequencies present in the process or present in the evolution of the time series. Now, we consider the cross spectrum and spectrum of sinusoidal models in this lecture. Before that, I will present a result which discusses how important the invertibility property is to if the condition of invertibility is not satisfied, then it may lead to same spectral density for two or more than two processes. So, first we consider the role of invertibility in spectral density, in identifying the spectral density. If the invertibility condition is not satisfied, then it may happen that two or more processes have the same spectral density. So, suppose we consider an ARMA PQ process, phi b y t equal to theta b u t, and it can be written as a general linear process also, y t equal to summation over j psi j u t minus j, where summation j equal to 0 to infinity mod psi j is finite, means the sequence of psi j's is absolutely convergent. Then we say that the process is causal. Now, suppose the roots of phi b equal to 0 are g j inverse, and then we write g j inverse equal to a j for all j equal to 1 to p, and roots of theta b equal to 0 are h j inverse, and we write h j inverse equal to b j. Then we can write the process as product j equal to 1 to p 1 minus a j inverse b y t equal to product j equal to 1 to q 1 minus b j inverse b u t. Actually, AJ's and BJ's are roots of the equation theta b equal to 0 or phi b equal to 0. So, you can write phi b equal to product j equal to one to P 1 minus A j inverse B, and you can write theta B as product j equal to 1 to Q 1 minus B j inverse B. So, using these relations you can write your process phi b y t equal to theta b u t in this form. Now, we assume that phi b and theta b are such that phi b theta b is not equal to 0 for all b such that mod b is equal to 1, and this obviously implies that no root is 1. If any of the roots of phi b or theta b is equal to 1, then for b equal to 1, either phi b becomes 0 or theta b becomes 0 or their product becomes 0. Then we suppose we have r roots of phi b equal to 0 greater than 1 in magnitude. So, we arrange those r roots in the beginning without loss of generality. So, mod of A j is greater than 1 for all j between 1 to r, and for remaining p minus r values mod of A j is less than 1. So, mod A j less than 1 for all j greater than or equal to r plus 1 less than or equal to p. Similarly, for theta b equal to 0 also, we assume that mod of b j is greater than 1 for all j greater than or equal to 1 less than or equal to s, and mod of b j is less than 1 for all j greater than or equal to s plus 1 less than or equal to q. So, s of the roots of theta b equal to 0 are greater than 1 in magnitude, and remaining q minus s roots are less than 1 in magnitude. Of course, for theta b equal to 0 also we have arranged the roots in such a manner that the roots which are greater than 1 in magnitude come first, and the last q minus s roots have a value less than 1 in magnitude. Then the spectral density function for the process y t is given by f y omega equal to sigma square u upon 2 pi product j equal to 1 to q mod 1 minus b j inverse e to power minus I omega whole square divided by product j equal to 1 to p mod 1 minus a j inverse e to power minus I omega square. So, actually we have substituted the values of actually this is the expression for spectral density function, and then we have written theta e to the minus I omega and phi e to the minus I omega as the product of these expressions, means 1 minus b j inverse e to the minus I omega mod of this square, and in the denominator we have taken product of mod of 1 minus a j inverse e to the minus I omega square. You can write phi b in mod of phi b square in this form. Let a j bar and b j bar be the conjugate of a j and b j respectively. We define phi star b equal to product j equal to 1 to r 1 minus a j inverse b, then product j equal to r plus 1 to p 1 minus a j bar b, and theta star b equal to j equal to 1 to s 1 minus b j inverse b into product j equal to s plus 1 to q 1 minus b j bar capital B. Then we consider the process phi star b y t star equal to theta star b u t. Then this process has the spectral density sigma square u upon 2 pi mod theta star e to the power I omega whole square upon mod phi star e to the power I omega whole square. Now, 1 minus b j bar e to the power minus I omega, and mod of this is equal to 1 minus b j e to the power I omega mod of this, and this is equal to mod of b j into 1 minus b j e to the power minus I omega. Hence, for y star we have the spectral density f y star omega equal to sigma square u upon 2 pi product j equal to s plus 1 to q mod b j square divided by product j equal to r plus 1 to p mod a j square. We get this term, and then in the numerator we get mod theta e to the power I omega square divided by phi e to the power I omega mod of this square. Then this term gives you, now this term along with sigma square u upon 2 pi gives you f y omega. So, then we observe that if we consider the process phi star b y t star equal to theta star b u t star, with u t star is a white noise process with mean 0, and variance we take as sigma square u product j equal to 1 to p mod a j square divided by product j equal to s plus 1 to q mod b j square. Then this process is invertible and it has the same spectral density as your original process phi b y t equal to theta b u t. Because suppose you write this quantity equal to sigma square u sigma star square u. Then the spectral density for this process is f y star omega equal to now in place of sigma square u, you combine sigma square u, in place of sigma square u, you have sigma star u square upon 2 pi. Then in the numerator you have mod theta star e to the power minus I omega square upon mod phi star e to the power minus I omega whole square. Then you can write sigma star square u in this form, and mod theta star e to the power minus I omega square upon mod phi star e to the power minus I omega square is equal to this quantity. So, actually this quantity gives you so, ultimately you write this ratio equal to this and you replace this sigma star square u by this. So, this term will cancel out and ultimately what you get sigma square u upon 2 pi mod theta star, you get theta e to the power minus I omega square upon mod phi e to the power minus I omega square, which is same as f y omega. So, this process is invertible, though the original process phi b y t equal to theta b u t is not invertible, and this process has the same spectral density as this process. But the variance of the white noise has changed. So, we observe that this process is also invertible. We have replaced by y t star by y t, and then u t star has the same u t star is actually the same white noise process which we have here. It has mean 0 and this much of variance. So, this process is invertible and it has the same spectral density f y omega. So, the original process was not invertible, but you can find a process which is invertible and which has the same spectral density as the original process. Just for example, suppose you have this process y t equal to u t plus 4 u t minus 1. U t follows a white noise process with mean 0 and variance 1. Then this process is not invertible. But if you consider the process y t equal to u t star plus 0.25 u t minus 1 star, u t star follows u t star is also a white noise process, but with mean 0 and variance 16. then obviously this process is invertible. Now, if we calculate the autocovariance functions of both the processes, then both the processes have gamma 0 equal to 17. You can easily verify it. Gamma 1 is equal to 4 and gamma k is equal to 0 for all k greater than or equal to 2. So, naturally, when you obtain the spectral density function of the two processes, you get the same spectral density for both the processes, which is f y omega is equal to 17 upon 2 pi 1 plus 8 upon 17 cos omega. Actually, we have used the formula for the spectral density of MA1 process, and then you can easily calculate the spectral densities for both the processes, and then you will observe that both the processes have the same spectral density. So, although the original process was not invertible, but we have obtained a process which is invertible, of course, with different parameters, and it has the same spectral density as the original process. Now, suppose you have two time series and both the time series have periodicities. Then you may be interested in whether the periodicities of two time series are similar or dissimilar, or there is as such no relationship between the periodicities of the two time series. How the periodicity of one time series behaves in comparison to the periodicity of other time series. So, we use cross spectrum analysis to evaluate the similarity and dissimilarity between two time series in terms of their periodicities. Usually, we use cross spectrum analysis for the signals that come from the same source, but it is not necessary. Any two signals that have the same data length can be evaluated using the cross spectrum analysis. So, basically it can be used for any two time series, but the time series have the same data length. Now, suppose you have two time series x t and y t, and we assume that both the time series have expectation 0. Then the question is if the periodicities are related with each other. The two time series have periodicities, and you want to check, you want to verify if the periodicities of two time series are related to each other or not. And suppose that the periodicities of two time series are related with each other, then what the phase relationship is between them. So, you are also interested in the relationship between the phase of two time series. Now, first we define the covariances across two time series. So, suppose you take the covariance between x t and y t minus k, then this gives you, say we denote it by gamma k x y. then this gives you the cross covariance between x and y. Now, notice that usually for two random variables x and y, the covariance between x and y is same as the covariance between y and x, but this may not happen with the cross covariances for two time series. Say if you take gamma k y x, then gamma k y x is equal to covariance between y t and x t minus k. So, in this covariance you are taking the current value of x and k period lagged value of y, and in this covariance you are taking the current value of y and k period lagged value of x. So, this may not be equal to gamma k x y. So, this thing you must keep in mind. Now, Fourier transform of cross covariances, or you can say cross spectrum, is you take, you denote it by say f x y omega equal to summation k equal to minus infinity to plus infinity e to the minus I k omega. You take covariance between x t and y t minus k, and then this is equal to summation k equal to minus infinity to plus infinity e to the minus I k omega gamma k x y. So, this is actually this cross spectrum is actually the Fourier transform of these cross covariances. So, once you take the Fourier transform of cross covariances, you get the cross spectrum between x and y. Then in general, f y x omega is not equal to f x y omega. Obviously, because in general gamma k y x is not equal to gamma k x y, and we define f x y omega based on gamma k x y, and we define f y x omega based on gamma k y x. F y x omega is the Fourier transform of gamma k y x. So, in general f y x omega is not equal to f x y omega. Then you have f x y omega, you can write it as summation over k e to the minus I k omega expectation of x t y t minus k, and then you can write it equal to expectation of y t x t plus k. So, still the lag between x t and y t minus k is the same, is t minus t plus k is k and t plus k minus t is k. And you write it equal to summation over L from minus infinity to plus infinity e to the power I L omega expectation of y t x t minus L, L is equal to minus k. So, here what you obtain, this is the Fourier transform of cross covariances between y and x, but you have replaced omega by minus omega, means you can write I L omega equal to minus I L minus omega. So, this is actually equal to f y x minus omega, or you write it equal to f y x omega bar. The So, this is the relation between cross spectrum of x and y and cross spectrum of y and x. F x y omega is equal to f y x minus omega. Using the cross spectrum, you can easily obtain the spectrum of a sum. Say, suppose you define the time series z t equal to x t plus y t. So, z t is the sum of two time series x t and y t. Then the spectral density function of this new time series z t is f z omega equal to summation k equal to minus infinity to plus infinity e to the power minus I k omega. Then you have expectation of z t minus k. And suppose this is the autocovariance function for z t and we denote it by say gamma k z. Then this is f z omega is equal to summation k equal to minus infinity to plus infinity e to the power minus I k omega gamma k z. Now, expectation of z t minus k is equal to expectation of x t plus y t, x t minus k plus y t minus k. And then if you take product of these two terms and then you take expectation, then what you get? You have x t minus k here plus x t y t minus k plus y t x t minus k plus y t minus k. And if you take expectation of this, then you obtain, here you get gamma k x plus gamma k x y plus gamma k y x plus gamma k y. Then you substitute these autocovariances and cross autocovariances here, take summation, then finally you obtain f z omega equal to f x omega plus f x y omega plus f y x omega plus f y omega. So, basically your z t has two components, x t and y t. So, say for example, if z t is a signal, then it is composed of sum of two signals x t and y t. Then we can decompose the variation in z t to different sources. Means this is the power spectrum of z. You have decomposed it into the power spectrum of x. Then the spectrum of x y, cross spectrum of x y, then the cross spectrum of y x and the spectrum of y. So, basically you have decomposed the spectrum of z into different components, different sources. This also decomposes the variation in z t in different sources. And suppose x t and y t are uncorrelated, then what happens? If x and y are uncorrelated, then if x and y are uncorrelated, then gamma k x y becomes 0. So, f x y omega becomes 0. Similarly, f y x omega also becomes 0. So, in that case f z omega is equal to f x omega plus f y omega for all omega. So, if x and y are uncorrelated, then and z t is equal to x t plus y t, then the spectrum of z t is simply the spectrum of x plus spectrum of y, means variation of z is simply the variation of x plus variation of y. Now, we can consider a simple sinusoidal model. So, suppose you have a time series y t equal to 1 to n, and this time series contains a deterministic sinusoidal component at frequency omega along with a random error term. So, we consider the model y t is equal to mu plus alpha cos omega t plus beta sin omega t plus u t. So, your time series contains a sinusoidal component, consists of this cosine wave and this sine wave. Here u t is a purely random process, mu, alpha and beta are the parameters to be estimated, and just for convenience we assume that n is an even number. Then you can write the model 1 in matrix notations as, say, suppose you write y equal to y 1, y 2, y n, and then you define matrix A as its first column is consists of 1, 1, 1, so on. So, the first column is corresponding to the intercept term. Then the second, for t equal to 1 you get cos omega, for t equal to 2 you get cos 2 omega, and so on. In the third column you have t equal to 1 sin omega, for t equal to 2 sin 2 omega, and so on. For t equal to n you have sin n omega. So, this is how we define matrix A. The first column is consist of 1s, the second column is consist of omega, cos 2 omega, so on, cos n omega. The third column is consist of sin omega, sin 2 omega, and sin n omega. Then u is equal to u 1, u 2, u n. Theta is consist of the parameter vector mu, mu is the intercept term, alpha the coefficient of cos term or cos, alpha is the coefficient of cos term, beta is the coefficient of sin term. Then for this model, the least square estimator of theta is obtained as A transpose A inverse A transpose y. So, this is the least square estimator of theta, theta hat equal to A transpose A inverse A transpose y. Then the highest frequency we can fit to the data is omega equal to pi, and the lowest frequency we can fit completes one cycle in the whole length of time series. Now, whole length of time series is n, and then corresponding to the frequency omega, the cycle length is 2 pi by omega. So, we equate 2 pi by omega equal, we write it equal to n. We obtain the lowest frequency omega equal to 2 pi by n. So, now suppose we assume that omega is restricted to one of the frequencies in this range. So, omega p is equal to 2 pi p by n, and p is equal to 1 to n by 2. So, for p equal to 1, what you get? 2 pi by n, the lowest frequency. Then for p equal to 2, you get 4 pi by n, 3, 6 pi by n, and so on. When you take p equal to n by 2, you get omega n by 2 equal to pi. So, pi is the highest frequency which you can fit to the data. We also make use of these results. Summation t equal to 1 to n cos 2 pi p t by n is equal to 0, and summation t equal to 1 to n sin 2 pi p t by n is equal to 0. And then summation t cos 2 pi p t by n cos 2 pi q t by n is equal to 0 if p is not equal to q. It is equal to n if p is equal to q equal to n by 2, and it is equal to n by 2 if p is equal to q, but not equal to n by 2. Similarly, you find these summations of sin 2 pi p t by n and sin 2 into sin 2 pi q t by n as 0 if p is not equal to q or p equal to q equal to n by 2, and it is n by 2 if p is equal to q not equal to n by 2. So, we require these summations to obtain the expression for least square estimator. Then the sum of sin 2 pi p t by n cos 2 pi q t by n is equal to 0 for all p and q. For n even and omega p equal to 2 pi p t by n, p not equal to n by 2, you have A transpose A equal to, now if you take A transpose A, then the first one element is n, then you have sum of these cos functions, sum of these sine functions, and sum of product of these two, sum of squares of these two, sum of this column, sum of squares of elements of this column. These are the things which you will require in obtaining A transpose A. And using the summations which I have defined from equation 2 to equation 5, you can easily verify that A transpose A is equal to this matrix. And A transpose Y, this is your A and this is Y. Then the first element comes from, you are taking transpose of this. So, first row is 1 1 1. So, you get summation y t here. Then in the second row you multiply by this, then you get summation t y t cos omega p t, and then you have summation of t y t sin omega p t. So, these normal equations then become, you can simplify the least square estimator actually in this form. Mu hat alpha hat beta hat equal to, you write A transpose A inverse here, which we have obtained here. So, A transpose A inverse, you get 1 upon n here, 2 by n here, and 2 by n here, and then you multiply A transpose A inverse by A transpose y, this term. So, finally, you obtain mu hat alpha hat beta hat equal to y bar 2 by n summation t y t cos omega p t and 2 by n summation o t y t sin omega p t. Then for p equal to n by 2, cos omega p t is equal to 0, and then you have this model. So, you remove the sine term, and cos pi t is equal to minus 1 to the power t. So, again you apply the method of least squares, and then you obtain mu hat equal to y bar and alpha hat is equal to 1 by n summation y t minus 1 to the power t. So, these are the least square estimators of mu hat, mu and alpha if you fit a sinusoidal function. Now, the total sum of squares is equal to summation t equal to 1 to n y t minus y r square, and suppose E t is the least squares residual. Then for the fitted model, actually you have mu hat is equal to y bar. So, you take y bar towards the left hand side, you get y t minus y bar equal to alpha hat cos omega p t plus beta hat sin omega p t plus E t. E t is the least squares residual. Then summation over t y t minus y bar square, this gives you the total sum of squares. Then total sum of squares is equal to summation t equal to 1 to n alpha hat cos omega p t plus beta hat sin omega p t plus E t whole square. And then you take square of this in this summation plus summation E t square, and you know that this cross product term will have expectation 0. This is the least squares residual, and this least squares residual is uncorrelated with this part. So, and this term actually gives you the residual sum of squares. And this is actually a explained sum of squares. So, we have decomposed the total sum of squares into the explained sum of square plus residual sum of square. Then you can further write this explained sum of square or sum of square explained by the periodic component as summation over t alpha hat cos omega p t plus beta hat sin omega p t square equal to, you get alpha hat square summation cos square omega p t, which is equal to n by 2. Then you get beta hat square summation sin square omega p t, which is again n by 2, and the cross product term is equal to 0, because summation cos omega p t sin omega p t is equal to 0. So, finally, you get this equal to alpha hat square plus beta hat square n by 2 if p is not equal to n by 2. And for p equal to n by 2, you do not have this term, and then cos omega p t becomes minus 1 to the power t, and then you can easily verify that the explained sum of square is alpha hat square n. And so, this is how you can decompose the total sum of square into explained sum of square and residual sum of square. Okay, so today we have discussed the cross spectrum, which can be used for comparing the periodicities or frequency properties of two time series x t and y t. You can also compare the phase of two time series if the periodicities are related to each other. Then we have also discussed the fitting of sinusoidal model, Your yT's consist of just a single periodic component, and then we have fitted it, and then we have observed that the explained sum of square is actually the estimated actually your explained sum of square is alpha hat square plus beta hat square into n by 2, and what is alpha hat square plus beta hat square? This is the square of amplitude of your sine and cosine wave. So, you can decompose the total sum of square into explained sum of square, sum of square explained by the sinusoidal component, and the residual sum of square. In the next lecture, I will consider the periodogram analysis, which is used for estimating the spectral density function on the basis of an observed time series. So, now I am going to finish this lecture. Thank you.
Hello, I am A.K. Sharma and I teach sociology in IIT Kanpur. You may ask, how do sociologists view religion? Religion is becoming an important issue for our society. Now, sociologists, this is true that sociologists explain one thing in terms of other things of society. So, religion, if you ask sociologists to explain religion, they will explain religion in terms of other things of society like education, economic development. In sociology of religion, there are two major traditions actually. In one tradition, to use language of methodology, in one tradition religion is a dependent variable. In another tradition, religion is an independent variable. What I mean is that in the view of Karl Marx, who said that religion is the opium of the working class, religion is closely associated with contradictions or relations of class in society. Marx believed that as time passes, societies evolve, and this evolution of society is dialectical, like from a classless society to a class society, class formation, and eventually again a classless society will emerge. Karl Marx believed that laws of human behavior or laws of society are specific to stage of development of society and are closely associated with mode of production or tools and techniques of production and ownership of tools and techniques of production. To Karl Marx, who think that a modern society is a capitalist society, religion is the dependent variable which needs to be explained in terms of class relations. And when he says that religion is the opium of the working class, it means that religion is used by the powerful class, the class which owns the means of production, to legitimize their class position or to confuse the workers. Let the workers think that if they are poor, if they are exploited, and if they suffer from various kinds of problems, it is because of their fate or their deeds in the previous births, and not develop the revolutionary consciousness to analyze the real causes of their poverty or exploitation or ill health. This is one view, and religion is the dependent variable, which also means that tomorrow in socialist society or in communist society, if it ever emerges and society becomes classless once again, religion may not exist. Now, according to another view, Max Weber, religion is actually the independent variable that explains emergence of something else, and that something else is the emergence of capitalism. Max Weber said that unlike in the Hindu countries or the Muslim countries or Christian countries where influence of Catholic Christianity was rampant, capitalism, as we understand by capitalist institutions, capitalism could not have developed. It does not mean that people, Hindus or Muslims or Catholic Christians, they were not acquisitive in nature, but there was a difference between them and those influenced by Protestant ethics in certain countries of Western Europe, and the difference was that these people did not use what they earned from their enterprises for comforts or for saving or for security or for status or prestige, but whatever they earned from their enterprise, they further invested this in the enterprise itself, and they lived simple life. By living simple life and spending the earnings back in the enterprise leads to emergence of capitalism in Western Europe. Here you see that religion is the cause. So, at some point of time, some philosopher, his name was Calvin, who gave a new turn to Christianity and propounded the philosophy of a new philosophy of Protestantism, also called Puritanism, the theory of predestination, which created anxiety in people's mind to know whether they are elect or not, whether after their death they will go to hell or heaven. So, this reinvesting in enterprise and not using the profits for their own gains or for their own comforts, this produce capitalist society or industrialization, in simple language industrialization, or this produce economic development first in the countries of Northwest Europe. And another issue which sociology tackles with regard to religion is whether we are secularizing. Now, it has been found that in the Western countries with urbanization, economic development, industrialization, education, democracy, there is a fall in religiosity. But in our country, secularization is defined in a different way, because we are a plural society, and for thousands of years all religions have been juxtaposed in our country. So, we define secularization as a process in which state maintains equal distance from all the religions, but does not become irreligious state. So, but this kind of definition or this approach of state obviously is going to raise new issues, new social problems and religious issues, other issues, but this is what it is. So, sociologists of religion will also study this process of tensions in the process of secularization in a plural country like India. Thank you.